We had thought long and deep about the two-body problem. Now let's add another one and have a look at a three-body problem. As you know, the three-body problem has no general solution, but there are some simplifications that one can do that lead to solvable systems. Some solvable systems are practical applications. One of them is the circular restricted three-body problem, which you have when the third mass is much, much smaller than the other two masses. So essentially a test particle orbiting two other bodies. So you have a circular orbit, a two-body problem, and you add a massless test particle to it. The concepts that I would like to touch on this particular example are the Jacobi constant and the Lagrangian points. The Jacobi constant is the only constant of motion for the test particle in this three-body problem. And the Lagrangian points are equilibrium points for this test particle. And the second problem would be the problem of the hierarchical triples. Hierarchical means that you can separate it in two binaries. You have an inner binary, and then you have a distant third object that is in orbit around this inner binary. So essentially, you split the three-body problem into two binaries. That's called the hierarchical triple. And one of the interesting effects that is happening here are Kozai-Lidov oscillations. Kozai-Lidov oscillations have become one of the most studied problems in all of astrophysics, since it has a lot of applications for exoplanets. So let's look at the circular restricted three-body problem. As I mentioned, the Jacobi constant is the only integral of motion for the test particle in this problem. The surfaces that you're looking at here are the surfaces of constant, the Jacobi constant. As you see, you have the orbit around the primary, or you have orbits around the secondary, or then you have horseshoe orbits that are neither in orbit around the primary nor around the secondary. And for other values, you have this tadpole orbits, where after the horseshoe closes around the L3 point. So let's see how to derive the form of the Jacobi constant. So consider that the acceleration of a particle subject to the gravitational forces of the mass 1 and the mass 2. So let's now pass to a coordinate frame that is co-rotating with the secondary. In this case, the acceleration in the rotating frame is equal to the acceleration in the inertial frame minus the centrifugal force minus the Coriolis force. If we align the angular momentum of the orbit of the secondary with the z direction, then in Cartesian coordinates, these equations become. So you can write the right-hand side in terms of a potential. So if we write this in terms of a potential, we obtain these equations. And the function u is omega squared over 2 x squared plus y squared plus mu1 over r1 plus mu2 over r2. So in this equation, x squared plus y squared is the centrifugal potential, and the term 1 over r1 plus 1 over r2 is the gravitational potential. So the partial derivatives of these are what give rise to the centrifugal and gravitational forces. And these terms here are the Coriolis force. So to get the Jacobi constant, we multiply the x equation by x dot, the y equation by y dot, and the z equation by z dot, and sum all of them. What you get is x dot dot, plus y dot dot, plus z dot dot, is equal to du dx x dot plus du dy y dot plus du dz z dot. And you will recognize this right-hand side here as the time derivative of u. It's the chain rule of du dt. So if you integrate the left-hand side in time, then you obtain x dot squared plus y dot squared plus z dot squared plus an integration constant. is equal to twice this function u. So there you have it. C, this constant of integration, is the Jacobi constant. So you can write C, give it a subscript j for Jacobi, that's equal to twice the function u minus x dot square plus y dot square plus z dot square, which is the square of the velocity. Now, if you substitute here the definition of u, remember these are velocities in the rotational frame. So the usefulness of the Jacobi constant can be appreciated if we consider the locations where the velocity of the particle is zero. So in this case, you have the Jacobi constant being equal to twice u. So this equation here defines a set of surfaces for particular values of the Jacobi constant. These are known as the zero velocity surfaces. For instance, here you have a set of different zero velocity surfaces. In here you have this surface, that's a zero velocity surface, this one, and the outer one here. And the dark areas, they are forbidden because these are areas where v squared would be less than zero. So the definition of the Jacobi constant is 2u minus v squared. So the v squared has to remain positive. So that defines areas where the particles cannot go. The particle has a motion that is bound by these surfaces and cannot go inside here. In here, the velocity would be imaginary. So even though the restricted three-body problem is not integrable, the existence of the Jacobi constant permits to find regions where the particles cannot be. We can see, for instance, that if a particle has a value of the Jacobi constant that is in orbit inside here, it can never orbit the secondary mass because you would need to pass from this area to this area. It can never escape the system either because you would have to cross an area where it cannot enter the forbidden areas. In this situation here, a particle that is orbiting the primary can actually go and orbit the secondary because it would cross areas that are allowed, but it cannot escape the system because you would need to cross a forbidden area. Notice that this defines also some special points. These are the Lagrangian points. As you decrease the value of the Jacobi constant, you are allowed more regions for motion. This is the first value of the Jacobi constant that this point here, the L1 point, is allowed for motion. So the particle can finally cross between these two areas. As you decrease further, you find the point L2 where you allow the particle to escape. You do not have any more this bounded forbidden region. Decreasing it even further, you end up with a horseshoe orbit. So the particle is going around here in a surface of zero velocity in the rotational frame. And then eventually, if you decrease the Jacobi constant even further, you unsplit here and you find this point where the particle can cross from this area in here to the area to the right of the diagram. And then you find the tadpole orbits as you decrease the Jacobi constant even further, defines the L5 and the L4 point. Notice that the L1, L2, and L3 points are unstable, whereas L4 and L5 point are stable. That is because if you place a test particle here at L1, even though it is an equilibrium point, it is surrounded by white areas where motion is possible. So if you place here, you can easily slip to these two areas. Whereas if you place a particle at the point L4 or L5, it's going to motion around the tadpole orbit. So the L4 and L5 point, because they are stable, they're very important. These are the location of the Trojan orbits. As you know, Jupiter is followed by a cohort of asteroids located in its L4 and L5 points where the orbits are stable. These L4 and L5 points are 60 degrees away in an equilateral triangle connecting the Sun and Jupiter.